Welcome to binary search trees, our first step into, well, more of our next step into trees. As we talked about before, we learned about the basic idea and structure that you had from trees, and now we're stepping down into a more specific example for one type of use, which is binary search trees. So binary search tree, or BSTs, is a search tree. Wow, how entertaining you said that, Kidney. Okay. A search tree is a tree whose elements are organized to facilitate the finding of a particular element. So we've seen before that we have the idea that parent to children and the edges and path and how things kind of subdivide down from one parent to a child. And so the idea with the whole family of what's called search trees is they allow you that the organization of how it branches is supposed to help you make it easier to find and discover information and add to it and maintain it. Now, binary search tree specifically is a binary tree, so being that every parent can have at most 2 children. We could have 0, 1, or 2, but no more than that. And for every node n that we see in the tree is that the left subtree of n contains elements less than the elements that are stored in the current one. So more the idea of whatever you have the data is and however you're comparing it is that anything that's considered to be the left child that's coming off of the actual main node is going to be values that are less than it. So that child and any subtrees that are in from there. And then the right tree, so being from the right child going forwards, will be values that are greater than the current node you're working with. So for example, if we had an insertion here, this is an example of a binary search tree where the data that's being stored here is just actually integers. And so if we start up here looking at the root of 45, you can see the left and then right children from right here that are attached to this parent. And the idea is that going down the left, well, 12 is less than 45 and 69 is greater than 45. And so this does match to a binary search tree. But what you also have is if we look at this subtree that's rooted at 12, so all of these nodes that we see below here down to the leaves of 25, 38, and 44, all of these are values that are smaller than 45. And the same thing here going for 69, that all the values past here are also then greater than 45. And the point of this is the fact that when you're searching for stuff is we now don't need to search through every piece of data. We now have, beyond just a linear structure to organize the data, we actually have this branching organization to keep subdividing the data as we go down. Because the same thing, if you're like, okay, if I'm searching for 30, you're checking at the root, and you're like, okay, well, no, 30 is less than 45, so I go to the left. We then see, okay, 12. 30 is greater than 12, so we go to its right child, and keep going down. 30 is greater than 15. We go here, okay, well, 30 is less than 42, so we go here, okay, 30 is less than 33. We go down to 25, and you're like, okay, well, 30 is not in there. And the idea is to get to there, we only had to search through 1, 2, 3, 4, 5, 6 pieces of data to discover that versus not having to search through all of them to detect this. So another example of that here is there's a visualization tool. You can see there's tons of these that are online. This is just one I found right now that we can go and start playing with. And I'm going to quickly play it. So this one allows you to do a lot of work and manipulate and visualize what's going on in building this. But we're now dealing again with another link structure here now that instead of being linear has this branching pattern that matches to an actual tree. And this one follows the rules of a binary search tree, being that when you start making the nodes that you have these 2 children at most. The one that's considered to be a left will be a link to a node in the future that's either blank or will be to a child that has a value less than the current one, and the right one will have a child that has a value greater than what's in the current parent node that we're working with. And so just like with the linked lists before, one of the cases you always deal with, and say we're going to start just doing some adds, we'll come to more things in the future, is that if it's empty, it just becomes the first node. So if this was a linked list, that's your start, your head reference right here. Now instead of trees, we refer to that start reference as the actual root. So if it's the first thing that's being inserted, it becomes the root. Doesn't matter what value. So here, we'll just suggest a random value to me, voices in my head. Okay, 22. Thank you, voices. 22. There you go. First thing, so it's 22. Now let's say I want to insert 10. What it's going to do is come and look and start at the root, just like you would start with a linked list. You begin at the root and you start moving in the right direction until you find the spot you need to actually do the adds. So we start here at 22 right here, and the idea is, okay, well, we're following the rules. Okay, I want to keep moving till I find an open location, so every new node will end up being inserted being a leaf within the actual tree itself. And we check, okay, well, 10 compared to 22, that is less than that data, and so we have to look toward this left child. Right now, if we look to the left, we can see there is no left child, so, oh, if there is no left child, just insert it there. Boom, boom. Same thing if I pick a value that's larger, like 33, it would go to the right and see that that one's empty and insert it. And even like this, now let's go for a smaller value. Let's, in between that would be 22 and 10, so I'll pick 15. The idea is smaller than 22, but then bigger than 10, and that's open. And start inserting from there. So we'll come back to this, but this is to show you that kind of visual structure of how things are built differently, that now when we're doing the inserts, it's no more at the beginning, at the end, or at the middle. Now it's you start in the beginning and you have to kind of continuously move forwards of going left or right until you find either the data you're searching for or the spot that where you can finally insert something new to the tree as a leaf, hopefully keeping stuff balanced. So let's go back to the slides. Right here and continue on. So key things to know about binary search tree is that the shape of a binary search tree depends upon the order in which the elements are added to the actual tree. Because it starts out blank, and then whatever is the first piece of data that's added becomes the root, and then everything after that starts deviating to the left or right, working its way down on each side, kind of zigzagging back and forth or moving in a line, whatever, to find an open leaf spot where it fits to the binary search tree definition. So the shape may also depend on any other additional processing performed on the tree to reshape it. This is called a balanced binary search tree that we're not dealing with much right now. We're just sticking with basic binary search trees. And it can hold any type of data so long as we can determine a relative ordering of that actual data. Now, using binary search tree, like why does this matter? Is it's basically faster for storage and retrieval of data. Something that we've been doing from the beginning of learning code when you learned anything about arrays, your basic lists, and our linked lists is just storing the data within here, so having a place to add it, organize it in some way, and then maybe search through that data to find a piece of data. And the point of what makes it different is like, well, you could use an array or a linked list to do similar action as the binary search tree, but the binary search tree has better like asymptotic complexity. So as the data grows and we need to do work with it more of doing more searches and more storage, as long as we get what's called like balanced within the binary search tree, that's nicely ordered, is that it'll be faster when we look at that time complexity. So if we look at things of like basic things of say adding something to the list, right here, linked lists, you know, that could take n, whereas binary search tree could take order n. Let's say contains is another big example. Just finding if something exists in a list. Is in the worst case for a list, it could be the last element within it. So you have to search through each one by one, and it could take n steps. Whereas for a binary search tree, if it's set up properly, you're always moving to the left or right of if it's bigger or less than, and effectively, hopefully, cutting out portions of the data, making it faster. And so if you're looking at that case, just comparing the contains, remember like n is like right here, that line we have going above, versus this log n. And so we have a case where, okay, yeah, at some lowercase values, the n will be faster, but once we keep increasing for the input sizes, well, you get this bigger gap between the two, and it means, okay, well, the contains for the binary search tree will run faster for us, and we can use this data structure instead to replace the original to actually make the program run faster if we need to deal with massive amounts of actual storage and retrieval. Now we can add operations such as find and add, and we need to know the rules for how these work. So the rules are known, unlike a simple binary tree. So this is why for a binary search tree we know how to add, where to add, how to do the search, and how to move through it. So the find operation, so just seeing if something exists in it, so this is like the contains or finding a piece of data or doing a get in this case, is a little bit more complex than doing it for a linked list. Or a linear data structure. You're doing that, you set up something, it steps forward one by one till the end, and if we reach the end and haven't seen it, then we're done. If we have earlier, you stop. It's a linear fashion. But now doing it for a binary search tree is first you set up a moving reference and you start at the root node. Next you compare the target data to the element at that current node. And what you do is, okay, well, if the data we're searching for and we're looking at the current node, if our data is less than the current node we're looking for, then you move to the left. So you take what's the left child. If the data is equal to it, you just stop and you found it. But if the data is greater that you're searching at compared to the current node, you move to the actual right. And you finish when you find the target node, so we've hit an equality, or you encounter the end of a path. So the target is not found. So we've gone all the way down to a leaf node, and it's still a value that's either bigger or smaller than that leaf node, and there's nothing else there, so we've hit the end. So like the equivalent of the end of the list. And I'll visualize this coming up soon. So find is determine if a particular value exists in a tree. New elements are added as leaf nodes. So this is adding to the node. So this is not the find. So this is adding. So we need to determine if a particular value exists in a tree. New elements are added as leaf nodes. So finding the correct add position is similar to finding an element. So we start at the root and we follow the path dictated by existing elements until you find that there's no child. So just like the find, you start at the root, you compare to the data. If it matches, you stop. If not, if it's less than, you move to the left. If it's greater than, you move to the right. Now when you try to move to the left and if there's no child there, okay, that's the open spot. That would then be where you insert that data. And vice versa for if you're moving to the right. So if you move to the right and there's no data, that you insert. If there is data, you move to that node and you do the same comparisons again, and you keep stepping down until you find that there is a new open location. So adding elements. So start at the root, compare to target element at the current node. If target equals the element, update data as found in the node or do nothing. Depends upon your design of it. If it's less than, move to the left. If it's greater than, move to the right. And if an open location is found while doing this moving, then add it to that location itself. Okay, so let's go now back to the visualizer and we're going to go through adding in the current data. So we're going to add in 77, 24, 58, 82, 17, 40, and 97 in that order, and seeing the resulting tree. Remembering that the structure of the tree is depending upon how you create this. So we've got the tree that we've had before. I'll go through now and just clear everything from this. So we'll go do the first insert. 77. It's the first node, so it'll become the actual root. Next we'll do 24. Right here, you see it comes in, compares, it's less than it, and there's no child to the left, so that gets inserted as the new left child off of the parent 77, which is the root. Next we're adding 58 here, which is come to the root. It's smaller than 77, so we'd move down to the left. Here, it's bigger than 24, so try to move to the right and see, okay, there's nothing here to the right of that child, so then it gets inserted there. So compare. Okay, less than, greater than, open, so insert. So far we have the zigzag pattern. Next we go with 82. So it's bigger, tries to move to the right, sees that's the right open, so it gets added to the right child of the parent 77. Next add 17. Boom, boom. So you can see 17 is less than 77, move to the left. 24 is bigger than 17, so it moves to the left, and here you can see the left was open, so it gets added here. So now 24 has both of its child slots, the left and right full. And next we're going to add 40. And so you can imagine where this would go. 40 is less than 77. It's greater than 24. It's less than 48, so to go into the left child of 58. And then finally 97, so back to bigger than 77, bigger than 82, so it should be to the right of 82. Okay. Now, if we go back and do some finds on this now for the actual structure, so we're just going to say, we're going to pick a value that is in the list, so we'll go 40. And the idea is the root is here, is it would start here at 77. So it would start at the root of 77, see, okay, 40 is less than 77, so move to the left. There is a node there, so keep going. Okay, we've got 24. 40 is greater than 24, so try to move to the right. There is a node there, so move to it. Next here, 40 is less than 58, so it'll go to the left, and then it matches, hey, fine, we have it here. So boom. We'll do a find 40. Boom, 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 boom. Found it. Right there. Now we can also try to do a value that's not there, so we'll try to go with 45. So same thing here is it's going to go, okay, well, less than from here, greater than this, less than right here, but then 45 is greater than 40, so we'll try to go to the right, and it'll see that there's no right child, so there's nothing in the list for it, so it is not found. So boom. And we can see it did that in 1, 2, 3 steps to find that, and it didn't have to go 1, 2, 3, 4, 5, 6, 7. So it didn't have to search through all of these. It did it in a smaller subset, so effectively doing it faster. Okay. Next, so example, just to visualize that again, what's happening is you have the 77, so if it's being added, it'll be the root node. 24 is going to go to the left of the root node. 58 will then go to the right of 24. 82 will be the right of 77. 17 will be the left of 24. 40 will be the left of 58. And 97 will be the right of 82. So same thing we saw before for the structure in the visualization tool. Now, what we have to also talk to is that binary search trees is one thing, but like I talked about it before that, like depending upon the way the data comes in, it changes the structure of it. And we want to have everything branching nicely so that every time we move to the left or right, we're subdividing chunks of the data and making the actual search space smaller that we're looking at for when we're trying to find the data. But what can happen is that as you insert data or remove stuff from the tree can turn into what's called a degenerate tree. So it's a grossly unbalanced tree, usually favoring one side. So this occurs if the input is completely or mostly sorted. So essentially degenerate trees turn into a linked list, and we don't get that log n that we're hoping for actual execution time. We only get n. And so this removes the value of using it all. And this is why you could start by teaching binary search trees, but then there's more complex ones that are called balanced binary search trees, things like AVL trees and red-black trees, that handle this case of degenerate things that could happen. So as the tree degenerates it rebalances it to bring it back and guaranteeing for you this overall good structure for searching for the data. Now, we're going to move on to a little bit harder step as always. We've had find, we've had like adding to a list, but now we need to do with removing elements from a binary search tree. And in this case, it is going to be combining stuff that we have with the find, but then once we get the node that we're searching for, well, then we need to actually take a step further and actually determine, well, what is the case of what type of node are we removing, and then deal with it differently. So similar to a linked list where you're dealing with the front or end or the middle. So not as simple as for a linear data structure. So after removing the element, the resulting binary search tree must still be valid, i.e. being that it must be a binary search tree. So the first step involves finding the node to remove. So same here as what you've done before the find. Start at the root. Keep comparing the data till you find a match. If you don't find it, you stop. If you do, you would find the node where there is a match and you're like, okay, stop here, and that's the node you want to remove from here. So starting at the root, comparing the data elements, moving to the left when it's smaller, moving to the right when it's bigger, stopping if you have to move to the left and there's nothing there, or if there is a match, then you just stop completely and you found the node that you now need to remove. So removing an element from a BST, you need to then, once you've found it, you need to determine what type of node it is and then delete it in specific ways. So we have three cases that we have to deal with. That is if the node to remove is a leaf, if the node to remove has one child, and if the node to remove has two children. So it's three cases detecting. So once you find the node, you just need to look at how many children does that node actually have, and then based upon that, you then decide, okay, well, you have to determine how you actually remove that node and update the tree properly. So you have these three cases. So example from right here, you have different situations. So if we're removing, say, 88, that's a leaf node, same as 85, 73. They're all leaf nodes because they have no children. This case here of node 51 has one child. You can see it's to the left. Same thing as 62, or like right here, there's 90 from this case here. And then other ones like 49 are the third case where it has two children here. Even the root in this case has two children. Like 86 here is two children. And so those are all different scenarios how you're removing it. But the idea is that we want to remove this node, but then we have to update everything around here to make sure that it still fits to being the structure of a binary search tree. So matching, because the only way that 88 here got to going to the left is because 90 was above it. So if we remove 90, we then have to restructure the subtree that's rooted at 90 to properly deal with that case. So first, leaf node. This is the easiest one to deal with. It's simple. This will involve unlinking from the parent node. You just simply delete that node. So you found it, you keep the data, but the idea is any links that you have from the actual parent down to the child, and if you have a backup link from the child to the parent, you need to just completely unlink it so that the parent is that their child, if it's the left one or right one, just depends if it's the left, you remove the left, if it's the right, removes the right, and it knows what to do from there. And this one here, if it has any links above, removes it. So simple. Leaf node, so it has no children, just unlink it from the parent. So node has one child, and what you do in this case instead is the deleted node is replaced by the child. So again, if it was a leaf node 57, we just remove it from right here. But what you have happen is if that's 51 is removed, and I only have one child, so there's not two in this case, that child then, the data from here gets moved up to this node. So the child node is deleted. In fact, well, this node you can say is effectively deleted, but we take the data from here and move it up. And so the idea is that, okay, well, this node is deleted, so 57 gets moved up. Here in this case for 90, it has one child, so 88 would be moved up from right here, and you have no node below. It's fine. Same thing here is 62. 67 would move up to right here, and then there would be no actual right child. Now, if the node has two children, in this case, you have to find an appropriate node lower in the tree and use it to replace that node. So the idea is here is like 86. is that, well, then you have, this is the subtree that's rooted at 86 from right here. And so you have to look down to the left or to the right to find a node that will replace it properly, that you still have everything to the right is bigger than that and everything to the left is smaller than it. Now, the way to do this is basically picking one of these two choices. So either doing what's called the in-order successor or getting the in-order predecessor. So it's a specific node that you find that's basically saying if it's the in-order successor, so successor being the one that comes after, is it's the smallest of the largest values. So you're going to the right, and then you're picking out of here, right here. So if we go down for 86, we want to remove it, and we want to get the in-order successor. So we're looking at the nodes that come to the right of it that are larger. And we look, okay, out of all of these, we want to look, okay, which is the smallest out of the largest values that's within here. So comparing 90 is bigger than 88, so 88 is the smallest. So 88 would be the in-order successor of 86. We move it up here. And the idea is, okay, well, 90 is still bigger than that would be the right, and well, everything else that's over here would still be less than 88. Now, you could also pick then the in-order predecessor, so being the similar idea, but being that you're going to the left, you're doing the previous of being smaller values. You're then looking to the left subtree and looking, okay, what's the largest of these smallest values from the fact is that, so you'd still order this. So in this case, if we're looking at 70, 81, 74, 73, 85, hey look, 85 is the biggest number out of all of these ones right here, and I want to replace it going up. But there's something that you're going to notice about these V patterns. If they're going in order successors, it's kind of just really going one down this way, then all down here. So this kind of V of like one to the right, then all the way to the left. And then you have the case of, okay, well, one to the left or all the way to the right. So we have to find those nodes. So you can see here in this case, 88 is the in-order predecessor and 85 is the in-order successor. And either of these nodes would be fine to replace it up here. But generally just follow one rule when you go this case is that for all nodes of 2, my implementation will take the in-order successor. So whatever you're told. And when you get an assignment on this, there will be a specific one that you have to do. Now, what happens after that is that you have to remove this node and it has to move up to 86. And so there's more work that has to be done. So here, basically, so here, in-order successor. To find it, the basic step is make one step. So if we did the in-order successor, make one step to the right, go as far left then as you can. Once you can go no further, this is the node that will be the in-order successor node. So for example, so in-order successor, one to the right, right here. So there has to be a node because, you know, we're removing a node that have 2 children, so there will be a left and right child. You go one node to the right and then as far left as you can. So if there was no more left right here, then 90 would be. In this case, there is one more, so there's 80, 88. So 88 is the in-order successor of this one. Now we'll remove the in-order successor from the tree, replacing the original node with the in-order successor. So the idea is that now 88 would have to be removed, and then it would be put up here to replace 86. So 86 would go up here where 88 is. But, so like example, if we were to remove 86, the in-order successor is 88, like I said. Now, removing the in-order successors, you're guaranteed not to have a left child for doing this, because the idea is you wouldn't have. If there's left child, you should have been able to remove once more. So the only thing you'll have is that either this is a leaf node, like in the case of this one of 88, between the actual two, or it will actually have a child that you still need to deal with. So example here is 60. If we're trying to get the in-order successor of 60 because it has 2 children and we need to replace it, we go one to the right and as far left as we can. There are no more left nodes, so 62 is the in-order successor of 60. But the problem here is that that has 1 child. It's not like 88 had no children, we could just delete it. This one has 1 node. So what we have to do instead here is 62 goes up to 60, and now we go back to our rule we had before when you only have 1 child, is that 67 goes where you saw 62. So let's generate a random binary search tree in the visualizer and then remove a node from each of these possible situations. So where you're a leaf node, where you have 1 child, or where you have 2, where you need to get the in-order successor. Okay, back to the visualizer. Let's reload the page so that there's nothing in here. I'm going to then generate a random tree that's minimum value of 5 up to, let's say, 100. Okay, we got this tree here. I want to just still do, okay, 1,000. I just wanted a bigger tree, so I regenerated between random values between 1 and 1,000, and we can see that we got this structure here. So now we need to go through finding each situation we want to deal with. So the first one is a leaf. So let's say for right now, I'm going to pick a different leaf that's going to take a little bit longer to go down to. So we'll go to 507. So we have that node right here. So if we want to delete that, you have the key. We need to start at the root and find it first. So bigger than, if 507 would be bigger than 371, would be less than 554, greater than 497 right here, but less than 509. So boom, we found a match. We can see it has no children, so this is a leaf. So this one just has to be removed. So this link from the parent of 509 down to 507 will be removed. So I'm going to select it here so that's highlighted in red, and then click the delete to tell it to go through trying to delete it. So first node found it here, would have done the search and say we've done the delete. So let's see that again. So for the example of 178, so let's do an example of 178, and we'll just do a find so you can see the search steps. So less than, less than, less than. Okay, that's the match. We have it there. We say, okay, well, I want to delete it. Just removes that link you saw from the parent that's above. Okay, the next scenario we had to deal with is where there is with one child. So say if we had 344, so we've searched for that, going less than, greater than, found a match. We check it doesn't have two children, but does have one child. So the idea here is that 346 would move up to where 344 is. So this is deleted from right here, and this one is then moved up. So 346, we delete it. Oh, let me insert that back in. 346, because I didn't want to delete that one. I want to delete 344. So I just want to get back to the situation we just had. So now it's 344 that I'm deleting. You can see then 346 moves up and gets linked to this parent. So same thing here. If we had, we wanted to delete 733, it's got one child, so the 863 would move up. And so that parent deleted its child, and then what was a grandchild moves up to being a child in this case. Now our last one is then to pull out the actual deleting of two nodes from right here. And so the idea is that we're just going to go with the in order successor. So if we're dealing with, like, we want to delete 554 and we want to get the actual in order successor for this, remember that it's going to be 1 to the actual, like, right, and then as far left as we can keep going. So we got here, there's one more left, and go down here. So 694 would be the in order successor of 554 and should be replaced by that node up there. So if I got 5 here, I can click on Get Successor, and you can see it finding that work. So here, so Get Successor. So 1 to the right, then all the way to the left. This is the in order successor, so this should move up here. We look at this, this is a leaf node, so this link here will just be deleted. 694 would then be moved up to here. So let's go and do that now. So I will click 554, do the delete. See, it's finding the in order successor, found a match, deleted it from right here, boom, moved it up. So good, right here. Okay, now let's set up a situation where it has to remove the child node. So we have, say, this in order successor right here from the actual left. So I will do just adding a new value within here. So I just need to have something that is less than 717 but greater than 6 here. So I will go with 710. Boom, boom, boom. Now this would be the in order successor because 1 to the right, another 1 to the left, and I'll even make it more to here. We'll do 708. So greater, greater, less than, goes to the left. So the idea here is 1 to the right and as far left as you can go. So now 708 is the in-order successor of 694. But now I'm going to set up a situation where there should be a right child. So if I do 709, so greater, greater, less than, greater. So we go with that one being at the right. So with this tree then, they still have the in-order successor for 708. So if I click this node and say get successor, 1 to the right and as far left as we can go. So it'll stop and it's at this node. Now in this case, before when it was just a leaf node, means we just remove this and the data goes up here. But in this case, this one is a child. So now this child of 709 has to go up where 708 was. And then 708, that data has to replace 794. So I'll go here. And then we will go delete. So you can see it getting the in-order successor. And this node places the data. This one then has to move up from that child, and the tree is still perfectly balanced from right here. So fun. We can even do the root node from right here. So in this case, it has 2 children. And so from here, as you expect, is you want to then move 1 to the right and as far left as you can go. So 442 is the in-order successor of 374. Ba. Ba. There you go. Okay. Gloriously fun. Now again, as mentioned before, is a degenerate tree is a grossly unbalanced tree, so usually favoring one side, and occurs if the input data is completely or mostly sorted. So essentially degrades to a linked list and removes all those advantages we had of subdividing the data and creating a faster find, research, and add, and all of that. So this removes that whole value of a binary search tree in the first place. So let's create one, and you can see what the structure starts looking at, and it really degrades to being more of like a linked list. So let's go through adding these in this order of 5, 8, 6, 7, 10, 12, 99. And you can see from right here is that we have a lot of cases of data that's partially ordered. Clear the previous tree here, and we'll start. So inserting first with 5 should become the root node. Insert 8 should become the right child of the root node. Six. Left should be the right of the parent, left of this. And you can see right now it may be branching, but it's still kind of a linear structure. If this one links to this, just one linear. It's not branching off as much between here. So doing a search right now would only be the equivalent of doing a linear search. Let's add 7. So this should be bigger, smaller, bigger. Smaller, bigger. So it should be to the right. Now this is still zigzagging, but look, it's still one to the next to the next. So still keeping a linear structure. Let's go and add 10. So bigger, bigger, bigger. So not as linear, but you notice even right now there's not much to the left, there's a lot more to the right, and right here there's a lot more clustering to the left of this actual node. So add 12. So same thing, still branches here to cut it down, but we're still getting these long sections here, and it's favoring one side versus the actual other side. Okay, so nice, and seeing that degenerate. So this is not so nice by the actual end. So you can see that in a basic binary search tree, it's good to use this for storage and retrieval, but depending on the data, the tree can degenerate. And that's why there's a whole family of other trees called red-black trees or AVL trees that actually deal with rebalancing the tree, as it's called, to make sure it keeps the optimal structure of what we would want for a binary search tree. So balanced binary search tree is that the find and add operation. So if a balanced tree, we have efficiency of kind of a log n. And this is the length of that longest kind of path. And as a tree becomes more degenerate, these operations approach more of order n. So our binary search tree implementation does not guarantee a balanced tree. So the shape of the tree is determined by the order that's coming in. So it could degrade, and we may not always get that optimal case. So there are implementations that ensure that a tree stays balanced, so things like AVL trees or red-black trees, but we're not going to be covering these in detail at all right now. I just want you to know that they actually exist. And most of the algorithms here make use of what's called rotations to balance it. So it uses things like the height and depth of a node to detect when something is becoming unbalanced. And when it is, it stops. So this is kind of after it does an add, and every time it does a remove, that changes the structure of the tree. It re-sees and says, is anything unbalanced within a certain level? And if it is, it goes through calling what these rotations to shift and change the structure of, they say, that subtree or parts of the tree to keep it into a nicely balanced structure. So if I switch back to the other screen, magically I have a different visualizer. So if you just search up AVL visualizers, we can see as we have the similar inserts and finds. So your add and find and remove operations are all basically the same, but you have a binary search tree. But instead what happens is after you modify the tree, so doing an add or remove, it checks these height and bands bounds and see does it need to restructure it around there. So let's start creating an imbalanced tree, and you can see how it'll start modifying it as we go. So to create a degenerate tree, we can start with just some ordered data. And so even if I just start inserting, say, 1, which will become the root, then I do 2. Here so far it's not so unbalanced. You're seeing where it's getting these weighted values to see, and if these go out of a certain range, then we can see, well, it knows that something wrong is going on. So if we go to 3, see there's a line, it can see that this is unbalanced, and you can see where it just did this rotation to change stuff around. So we can do that again if we keep trading this. So if I insert 4, this will go to the right. It's still okay that there's not too much balancing, that between any node here it's equal. So those that you can see the 3, the 2, the 1, but knowing the differences. But if I keep making this longer on this side, it means it's favoring this side versus this one, and it's going to detect that there's probably something wrong right here compared to the rest, and so then it needs to rebalance, which is, hey, for longer here, this one falls down, this one goes up, the other one continues on. So if we go with 5, boom, 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 boom. Oh, something's wrong, so shift it around. And so notice it still has that everything is a structure of being a binary search tree. So I can start doing a find to get the 5. So check, 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 done. So even though there's 1, 2, 3, 4, 5, it only took 3 steps to actually do that insertion. And so it'll keep going through all these insertions. This is even if we insert. So we can go for some smaller numbers. Let's go, so in my okay, from right here, -2. Right here. But now if we start deleting stuff, we can see where we're at. So if I say 4 is what I want to delete, so that thing has 2 children, we'll try to restructure and get, and so in that case it took the in-order predecessor to start doing the remove. But say even if I get 12, it's going to start creating potentially cases of, okay, I'll delete the 2. Deletes the root. Finds the balance. If I delete the 1 though, we start favoring that this is balanced over here, this is not, so it's going to shift stuff around. So I'll delete the 1. And you can see how it shifted it around to make it nicer again as well. Same if we delete 5. Restructures it. So the idea, and this is an algorithm you can look up, and is doing these rebalancing and reshifting on smaller parts. That so when you're doing adds, occasionally it does these reshifting, but then once you're done doing the add and remove and you're doing finds, it makes guarantees that the find will always be log n. So for right now, I shall stop. It's been 1 hour here for the video. I suggest you go through practicing some of this, thinking about, well, how would I start implementing that based on what we've learned about linked structures and dealing with detecting what you're doing. and going on to the next task that you need to solve. But if nothing else, especially this time of year, remember that no matter what grades you have or how things are going, I still think you're a good person. And if you think you're not, that just shows you maybe you have some room for improvement, and you need to accept that you are a good person no matter what you actually think, and just keep stepping forwards and knowing that even when we do something wrong, we should learn from it and try to make ourselves better and try to take care of the people around us. And learn more about trees. Let's stop.